To build a robot, engineers have to choose exactly how it moves. An industrial arm executes a rigid, high-speed stop with millimeter precision. Conversely, a soft robotic structure absorbs the impact of a falling weight without breaking. You rarely see a single machine do both well. The actuation trilemma balances three variables: power density for continuous force, control bandwidth for tracking speed, and compliance to yield to external forces. Materials dictate a strict trade-off. Pushing from massive power density with heavy metals collapses compliance, making the system completely rigid. Modern mechatronics escapes a trap through hardware-software co-design. We will construct a modern robotic joint from the ground up, starting at the physical plant, moving through mechanical linkages, and capping with control loops. Finally, we will see how diagnostic AI sits on top of this entire structure to guarantee operational fidelity over time. Modern robotics relies on architecting a layered mechatronic stack to force physically flawed hardware into high-fidelity compliance. Three primary drives dominate the physical plant: the electric brushless motor, the hydraulic cylinder, and the pneumatic artificial muscle. The electric motor provides high continuous power density and precise torque regulation. Hydraulics deliver massive force, but their physical response is sluggish. When intrinsic safety and human interaction are the strict priorities, engineers turn to pneumatic artificial muscles. These offer lightweight, naturally compliant behavior. A pneumatic system's pressure response exposes its primary drawback. Highly nonlinear inflation and deflation dynamics destroy trajectory-following fidelity. To make pneumatics usable, engineers write fast inner-loop pressure regulators using pulse-width modulated valve control, forcing acceptable bandwidth out of a sloppy plant. Selecting the foundational actuator locks in the baseline physical constraints of the entire robot. The precision burden transfers immediately to downstream components. Next up the stack is the mechanical transmission, the linkage that connects the raw actuator to the physical load. Gear trains and harmonic drives provide high stiffness and compact torque multiplication. But metal meshing with metal introduces physical backlash and high-frequency resonance. Belt drives eliminate that backlash and lower costs. The trade-off is torsional compliance. The physical stretching of the belt injects severe dynamic vibration into the system. Traditional engineering would attempt to solve this by installing heavier, stiffer belts, adding mass and cost. Modern drive systems deploy an algorithmic alternative: modal predictive compensation, or MPC, applied directly at the control layer. This visual demonstrates MPC in action. The algorithm forecasts the exact torsional vibration and preemptively alters the motor torque. This digital command physically cancels out the belt stretching in real time. Cable-driven transmissions present a similar problem. The nonlinear elasticity of the cables requires specific control schemes to constantly enforce positive cable tension. Software compensation is now highly preferred over physical mechanical redesign to improve torsional angle tracking. Engineers accept these mechanical compromises to keep systems lightweight and cost-effective, using control algorithms to act as a digital equalizer. Predictive math is useless if it arrives a millisecond too late. The electronic logic layer requires deterministic, ultra-low latency execution. This hardware architecture uses an ARM and FPGA node. The ARM CPU manages high-level path planning, passing data to the FPGA for time-critical inner loops. The FPGA parallelizes field-oriented control, allowing synchronous multi-axis operation across all robot joints without processor bottlenecks. This high-speed processing becomes critical when operating rigid electric drives near human workers, where an unyielding arm could cause severe injury. To synthesize physical safety, the control layer runs advanced algorithmic impedance tuning. Engineers deploy specific tools, like GPR-assisted NADM optimizers. The exact moment the robot contacts a variable stiffness surface, this optimizer dynamically manages force tracking. It prevents overshoot, forcing the rigid motor to react softly. The computing interface is the vital bridge. It forces unyielding hardware to behave compliantly in complex environments while preserving its massive baseline power. Even with advanced math, there are extreme operational environments where software compensation cannot overcome the physical limits of a single actuator type. Consider an agricultural apple harvesting robot. It requires millimeter spatial precision to navigate branches, combined with physical compliance to gently grasp fruit without bruising it. This hybrid architecture combines an electric outer loop with a pneumatic inner loop. The inner loop regulates pressure for a pneumatic end effector, providing a gentle, compliant interface. The outer electric loop handles the rigid, high-bandwidth spatial tracking required to navigate the entire assembly. This hybridization scales up to locomotion. Advanced designs integrate thrusters with wheel-leg mechanisms to bypass obstacle constraints, trading power management complexity for extreme mobility. True environmental robustness requires abandoning single-plant purism. Engineers must blend entirely different energy conversion physics into a single machine. Deploying these complex drives requires one final layer, guaranteeing operational reliability and preventing microscopic hardware failures. The control layer provides a hidden benefit. The precise data used by the modal predictive compensation to correct vibration inherently acts as a real-time health indicator for the mechanical parts. This diagram shows the data flow pipeline. The system passes this vibration data into a SHAP-informed multi-layer perceptron network. This explainable AI learns the nominal, healthy dynamics of the system. It catches subtle, discriminatory faults in the motor brakes and reducers long before catastrophic failure. We can now view the complete stack. We start with the brute physics of the actuator plant. We attach the intentionally compromised gear or belt transmission. We command that hardware through the deterministic control driver, and finally cap the system with the predictive AI network. The modern robotic drive is a layered stack, where advanced algorithms and predictive AI override the limits of basic physics.